When we talked earlier about going from an analog signal to a discrete or digital signal, we talked about the idea of sampling that signal. So, for example, I might have my continuous analog signal here in yellow, and my discrete sampled signal would be marked by red X's here. There's some important definitions to know when we're talking about sampled signal that we have mentioned previously. So the distance in time, so this is a time axis down here, the distance in time between two sampled points I'm going to call delta t, and delta t is going to be my sampling interval. What we're going to focus on when we talk about the consequences of sampling is that sampling interval, and perhaps more importantly, 1 over delta t, which we're going to call the sampling frequency. And the question that we're trying to answer with our analysis is how fast do I need to sample to accurately reconstruct the original signal? So let's go through a couple case studies to really understand the consequences of this sampling frequency. So here I've got a 10 Hertz sine wave, and these vertical divisions here correspond to a sampling interval of 1/100th of a second, or sampling frequency of 100 Hertz. So if I start sampling this signal at that particular sampling frequency, I now have a sampled signal represented by these red dots. And that's a signal that's been sampled at 100 Hertz. And remember, the original signal was a 10 Hertz sine wave. And to understand what that sampled signal is telling us, we're going to think about how we might reconstruct it. And right now we're going to use a linear interpolation, which is just drawing a line between my sampled points. So I have a line between those 2 points, and so on. Now I hope that you'll agree with me that even if my lines aren't very straight here, and we could certainly do a better job than a basic linear interpolation in reconstructing our signal, but I hope that you'll agree with me that this orange signal now, which is my reconstructed signal, looks pretty close to the original signal. So I would say this is a pretty good representation of the original signal that I got from these sampled, from that sampled signal, the red dots there. Okay, now I'm going to slow down my sampling rate. Instead of sampling at 100 Hertz, I'm going to sample at 27 Hertz. And as a consequence, my sampling interval has gone up too, from 0.01 seconds to about 37 milliseconds. And now these vertical lines are representing that 37 millisecond sampling interval. So if I take my sampled signal here, which remember I'm taking a sample every time my signal intersects one of these vertical lines, because that's the time that I know that I want to be sampling it. So that might be achieved in an Arduino if I used a delay 37 for delaying 37 milliseconds and did an analog read every time through the loop. Okay, we have a number of samples now of a number of cycles of my original signal, and I'm going to go ahead and reconstruct it using that same approach of just linear interpolation, drawing lines between the samples. So I'll draw a line between the first 2 samples, draw a line between the second 2 samples. Okay, and I think you'll agree with me that this reconstructed signal is not nearly as good as when we had a sampling rate of, or sampling frequency of 100 Hertz, but you know, the basic idea behind the signal is still there. I still get a peak in my sampled signal approximately every 37 milliseconds or so. And so this is still a, somewhat reasonable representation of the original signal. And obviously I could do a much better job of it if I reconstruct it in a better way other than just this linear interpolation. Okay, but now let's slow it down even further. Now instead of every 37 milliseconds or every 10 milliseconds as I did at 100 Hertz sampling rate, I'm going to sample every 83 milliseconds. And that corresponds to a sampling frequency of 12 hertz. And remember, this is originally just a 10 hertz sine wave, so I'm sampling very close to the original frequency here. And these vertical lines now are representing, on that 10 hertz signal, sampling every 83 milliseconds. So I'd take a sample here, 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 back up here. So these red dots now represent my sampled signal. I have 1, 2, 3, 4, 5, 6, 7, 8 samples of this particular time window of signals. And once again, I can reconstruct it by doing this linear interpolation. And what you can see from this reconstructed signal is that it looks absolutely nothing like the original signal, the original 10 hertz sine wave in black. In fact, this orange signal now looks like a 2 hertz sine wave. And that's a really kind of bizarre consequence of slowing down my sampling rate for my signal. So let's look into how we can avoid this kind of bizarre consequence and where this happens to come from, this weird 2 hertz reconstructed signal from an original 10 hertz sine wave that was sampled at 12 hertz. So the Nyquist-Shannon sampling theorem says that to accurately reconstruct a sampled signal, the sampling rate, or fs, has to be greater than twice the maximum or the highest frequency in the signal. And another way of writing that is fs has to be greater than 2fm, where we define fm as the maximum frequency in the signal. And yet another way of thinking about that is in terms of sampling interval, delta t, and delta t has to be less than 1/2 times that maximum frequency. So if I follow these rules, I should be able to accurately reconstruct the signal. And in that last example, the maximum frequency in my signal, it was a 10 hertz sine wave, so the maximum frequency was 10 hertz, and so I needed to be sampling at least 20 hertz. And so 12 hertz was clearly below that 20 hertz limit.